Hello, it's me again. Of course, whoever's watching, thank you for watching. Students, I know I sound like a professor, but to the guy I'm talking to, I'm not going to say his name. Some other guy I'm talking to from Embry-Riddle asked me to do something related to Lagrange equations and, well, Lagrange dynamics. And this, I said, I can, a basic introduction, what I'm learning in now. I'm not fully done with the full week, but I have about, I think I have about, let me see. Shit. Excuse my language. 1, 2, 8 more lectures left and 3 more quizzes. 2 more lectures are about examples, rolling wheel, falling ring, and then there's other examples in routine reduction. I mean, this is amazing. Yeah, but I'm gonna be talking a little just about Lagrangian. I keep saying Lagrange dynamics or equations. So I'm gonna set my phone down. I'm gonna try to make this simplistic as possible, but okay, okay, hope you guys can see. Okay, I'm gonna start from this section here. Please stick down. There you go. Okay, just give me some uniform. Okay, so Lagrangian equations very used for finding out specific. What is it? Mainly used for finding different. A general understanding for, oh my gosh, I'm sorry, whoa. I just knew this. It's not for specific coordinates. You can use it for Cartesian, cylindrical, and other different types of coordinates that I've learned. Find the object, the orbital motion, I think. Okay, that's not the point. Little coordinates. Here, the constraint force, non-constrained. So we're recalling the Albert's principle form because sooner or later we need to get a basic understanding of the forces applied for it and then follow up with the constraints. Sum of the net forces times the partial equals the forces, working forces on a body, equals the function of partials, and then there is constraints to the nth. Then we do elimination, constraint of the dot identity, or is it, yeah. There's no dot here, yes, no. Dot identity, constraints. Then to develop the Lagrange equation, we need to investigate formation of kinetic energy. This, I wrote down here, is the basic Lagrangian variable. Well, there's Lagrangian multiplier over there. This is the eigenvalue. Kinetic energy, which is T, minus potential energy, is broad what it is to find. So as we know, kinetic energy equals 1/2 mass, or the forces, net of mass, force, times the inertial vector inertial coordinates, position coordinates, position vector, inertial position vector, I'm sorry. We follow up here, partial. First, the only difference here is just a matter of the dot product and the base. Still, I need to run this quick. We need to take a derivative to match the Lagrange equation. No, not to match the Lagrange. Let me see real quick. It's shit. It's related to the Albert's principle, not the Lagrange equation. Take a derivative here, plus m derivative r partial Here is the same, but there, as we know, we need to know here, we see this, we know that MR is just force plus, doesn't matter which order. It's just the forces combined. We plug in that factor. This doesn't change. And here, let me show you here. Get out of the way. I hope you guys. Here. We just continue along. This is the function. MR, this is change, we move down. dt partial equals this. So we know that. Okay, for this, I can get an example of this as we found. As we know, 0 equals FCI delta R. We can say 0 equals FCI times Newtonian I J I delta Q J, which just equals to vector here. Say summation. It's funny. So 0. As we see, we find here. And this equals out to 0. Find this, and this is the Lagrange equation. Note, be careful in the future when you have certain forces applied with it. This equation is equal to 0 if there's only non-working forces applied on the body. Working forces, be careful in the future when you find gravity. Gravity tends to, so once you need to account to potential forces, gravity, and you need to account on this and then some other stuff that evolved into it, that can give complications and it can make your output wrong and count gravity twice when it should be counted as once. An example here, this is going to be recalled, this is going to be a step furthermore. This is going to be the third try of finding another try on particle rotating table. It's really cool, but I think there's other examples, and I realized I skipped a step. I'll just recall over here. Oh, it's been 8 minutes. Whew. Okay, so we're defining Lagrangian equation, conservative forces. It's really not hard. Recall generated forces, constraints, function dot equals function partial. Okay, so here, constraint conserved, fi partial, or no, it's just if the forces are considered or conserved, then the partial, potential forces will be a gradient potential forces, which equals out this. Generalized forces then become sigma forces equal out. We plug in this. This is using the chain rule, and since we have this canceling out the reason why we don't have sigma here is because we cancel out these. And what happens if we plug in 1 or 2 and it depends on 1 or 2? If it depends on 1 or 2, we got to that includes the sigma. So cancel out sigma because this is correlated with this. Then we just get this output here. I'm kind of not making sense. I just learned this today, so do your own self-study, man. But still, I'm not finished. Compared to d over dt here. Lagrange equation we found here. Okay, cards. Okay, this is just recalled from before. If you watched the last video, it was about the Alpers principle. What difference here is just the rate Rate 1, x beta. Here are the constant force. Here in the negative times the change of the displacement. R potential, non-orthogonal. So this really just not cancels. Oh yeah, it does. Yeah, it cancels out. Tend to be 0 because it's non-orthogonal. This gives negative c it. X energy functions. K1, mass 1 plus mass 2. Okay. Change mass r dot theta squared. This is just to understand the forces, the potential energy of it, or whatever. And then cosine. So that will be usually sine, but if it's cosine because it's non-arbitrary, non-orthogonal. Here, I mean, what's given here, you can use this common set of physics, and then here's this identity you tend to use because it gives a good representation of what we can use as reference here. So if we plug in 0 here, it gives 1 minus 1, cancels it out. So we can use the reference angle here, not initial. Here, they use the reference. So we just plug in 0 and so forth. Solving. This is solving it. Recall the energy functions. Recall the Lagrangian equations. Basic evaluation and so forth. And you really just plug in, understand what is being plugged in, understand how to, basically the algebra of it. Really not as complex as you would assume. This, I mean, the future, when you have the particle, I'll talk a bit later, you have sigma, not sigma, you have omega equaling to theta, which if you have this and then you plug it into a kinematic constraint, then it'll cancel out this and it'll make this more complex. Constrained dynamical systems, okay. So what we do, recall the virtual work from before Diopler's principle. The only difference is we have a minus force here. We just like F equals MA or F equals MR, then we just minus MR to that F. Virtual displacement. I kept this note here. Note this, we need to understand the identities. So right now we understand this, respect to this. Okay, I was just making sure I didn't forget anything. I need it, whoa. Wait a minute. Whoa, wait a minute. Okay, that's wrong. Okay, sorry. If you guys seeing. So what we do is just do some algebra here, plug in our identity or what we found before, factor out what we can. Then as we know, Q equals the function. This we can get it from here. Q, where is it? Q, no, sorry. This equals, yeah, right? Yeah, this is Q, because you can recall from Diopler's principle, the last video, from Diopler's principle gave us this understanding that the sum of the forces dotted the partial equals the forces worked on the body. Minus, because we just like around, blah, blah, blah. Okay, this is independent. If it's dependent on some other stuff, some other dependencies, I forgot, but then it will not be equal to 0. This is independent. This equation is independent. We get that. Plug in our new foundings equals 0 is independent, and we get our virtual work. This is constraint. Furthermore, we're gonna recall the Lagrangian multiplier rule, and then we're gonna just we're gonna plug in what we found from the Lagrangian multiplier, which can help us find the. Let me see. I know it's finding the object, or why can I not remember this? That was that. Our independence, yes. Accounting for Prothean coordinates. No. Augmented cost function. Prothean coordinates. This is just understanding. So once we get into furthermore aspect here, we're gonna use these little identities here. Generalized Q, perfect constraints. If we're talking about rates, or rates are just like this, and then states are just like this, anything respect towards. Long trajectory. What is it called again? Shit. I'm sorry, I was just trying to instantaneous virtual displacement. It must satisfy equal to 0 delta. It's a matter of taking root as well. There's a pattern here. I mean, you can see. Okay, so let's recall Lagrange multiplier. Optimize phi of the rates. D phi is really just replacing R. This is really just replacing it. If constraints are passed, equals 0, in which this can just equal to. I was gonna make sure it was like. So it's really the same thing as this, but it's with K. So it's like this. Okay, equivalent optimization, uppercase psi equals that, the Lagrangian multiplier psi k. Okay, we found this, as we know that, psi. And then we recall the work, the virtual work. We plug in our Lagrangian multipliers that we found, plug it in. Then we get this final equation. And then this is just respect. It's just a matter of the same thing as here, right? Yeah. Set of n plus m. Differential algebraic equations for the unknown variables. Rates with function of time. Lagrangian multiplier function of time. As we can use an alternative version for Lagrangian. It's just a matter of replacing the Lagrangian for Lagrangian equations. This. Okay, so I hope you guys can see this. Okay, basically we have angular momentum as well. Omega, R, ER, E theta, ER. Okay, mass, non-linear spring. This is a non-linear spring. Normal force. And the first way we can try this, there's 3 different ways. I would say my way of doing it is probably using, I would probably use the constraint Lagrange equation. This is just from before here, but it's like not as defined on that. These are not given over there. What is it called? I keep forgetting it. I don't know why I keep forgetting it. What is it called again? Okay. I forgot, but these are really good to understand. It makes a lot of stuff easier because it can give us the understanding of just generalized coordinates, some force we can use. I'm not fully familiar with it. I need to recall. I took a quiz on it earlier today. It was early this morning. I was really tired. But I will watch this video again. Anything that I'm very stuck on or some forth, I will make a next video clarifying it, which most likely will be this weekend, Saturday or Sunday, most likely Saturday. Make some calls Saturday and so forth. But beside the point, let's go back. I would probably not do Newtonian. Okay, so we have this force equals ma, or ma is Keynes, mr is Newtonian. Kinematic equation, r double dot minus r theta squared, er, respect, we understand the functions here. R theta double dot plus 2r, there's no other reason why we don't use cosine or sine, there's no, height, whether, how do I put this? You know, the person that's watching this, you guys know. We take the kinematic constraints, plug in omega, which cancels out this. What I mentioned earlier is that it would cancel out. Plug in this. Now we need to understand the forces applied on the mass. Sorry. Understand force R. Plug in R. This factor out a negative. Then we understand what the force is, just F sub theta, and then EOM, I think, is energy of momentum. I think becomes this equals M plug in R, which is just this. It's just F equals MA. It's really that simple. MR. M factor plug in our R. Plug in our R into this, and then our F value we found is that. It's not hard, it's just understanding the concept. And you really just do a kinematic constraint, solve for everything, use some algebra, and you get this final vector. Your final terms to calculate the net forces, and yeah. I'm not fully sure because I can find this, but it's just really just understanding other coordinates. I think so. Is this simplifying it, just using that? He wasn't specifying, the professor. I don't know. Okay, second try Lagrange equation. This is third try, but that I'll tell you later in a bit. It's 23 minutes. Shit. Okay, I don't want to make this too long. We take kinematic constraints. We get omega. Omega, this is out. This is our kinetic potential energy. This later on is going to take a gradient, and then it can equal out to this. Lagrange equation, Lagrange variable kinetic minus potential, 1 minus r squared. K1, really just plugging it into factoring using some algebra. Here, this equation is manipulated into plugging it to here. It's just manipulated into using some other algebra. Note for F sub theta in this problem is a non-working force. It's a non-working constraint force. So we need to know F sub theta equals 0. So delta R E sub R equals 0. Lagrange equation, plug in our findings, and we get that final to 0. Okay, this is a what is it called? Redundant subject. Let me try. Redundant set of coordinates subject to constraints. Constraint of Lagrange equation. Understand the rates. Okay, positions. It's all the same process right here. Same process, just manipulating and understand that you can recall these two identities, which are from here. From over there, you remember, I forgot, I think, over there somewhere. Since it's understanding rates, it's not, so if it was states, depending on, if it was states, like dot states, then it would be holy mnemonic constraints. Profane position constraint expression, which is just theta minus omega. A, this is understanding not for rows, it's for columns. Understand B and negative omega. Let me hurry this up. Recall the Lagrange equation. Understand this, respect down to R, the first position coordinate, first coordinate, and plug in 0 as our first column. We get that, the final result. Plug in 1, the final with theta, and you get that. This is coupled, still coupled. So we're gonna need to do a kinematic constraint, plug in, manipulate, and this is our final result. Yeah, it's that. Understanding concepts as well. I'll clarify some things in the future. This is generally what I've wrote down today, what I've learned. Sorry, I went a little quick on the little fast part, but I don't want to make this too long. It's almost 30 minutes. So, yeah. Till next time, this weekend or following. Thanks for watching.